We are finishing this first half of chemistry with molecular compounds, and these are going to be compounds that have covalent bonds, and we're also going to learn how to write their formulas, how to name them, and at the very end we're going to learn how to write formulas and write the names for acids and for bases. So if we get started with molecular compounds, just some general information about them. We know ionic bonds at this point. Between a metal and a nonmetal, one gives and one takes electrons. Covalent bonding is a lot different, actually. Covalent bonds are going to be between elements or atoms, but they're going to be sharing electrons. So no pluses or minuses anymore, because we're not losing or gaining electrons. So you're not going to see plus charged or negative charged ions. We call a molecule a neutral group, neutral meaning that the electrons are balanced, so we're still going to be meeting that octet rule in most cases. There are a few exceptions we'll get to, but it has to have covalent bonds. So ionic bonded elements, they're called compounds, but they're not called molecules. That's only for covalent bonds. Now, when you see the word diatomic, I want you to think of the word the prefix, di. The prefix di means two. So when we have this diatomic molecule, it's two atoms and they are bonded together, and specifically diatomic molecules are usually referring to atoms that are the same that are bonded together. So for example, there are 7 elements on your periodic table that will never be singular. For instance, you'll never have an atom of hydrogen. It will always have at least 2 that are bonded together, or you could have hydrogen bonded to other elements. But if you just have hydrogen, it's not stable enough to be by itself, so it has to be bonded at least to another hydrogen. And these are the 7. These are diatomics. Whenever we say oxygen, for example, if I said, all right, you have oxygen, and you have to write that down, for instance, maybe in a chemical formula, you would always put O2. You can never just have O by itself. It doesn't. It's not stable enough to be by itself. So those diatomics are incredibly important, especially when we do get to balancing equations and things in the second half of chemistry. You'll see these words by themselves, and you'll need to know to put that 2 with them, since they are diatomic. And then this is just a picture. Obviously hydrogen being very small because it only has 1 proton in it, whereas iodine being very large, and so the atom of that is bigger. So you can kind of see their their increase in size there. When we look at molecular compounds, very similar to what we had with ionic compounds, it's going to be a compound that shows the symbols and the formulas, the numbers, the subscripts will tell us how many of each one we have. But when we're specifically looking at these molecular compounds, so covalent bonds, we have different properties than we did with ionic bonding. Properties of covalent bonded compounds: we have lower melting and boiling points. They're lower because covalent bonds are very strong, but yet as far as the energy it takes to break those bonds, it is less than what an ionic bond would be. We have mainly gases and liquids. We don't have very many solids at all at room temperature, so lots of liquids and gas examples, and they are made up of nonmetals. So you're never going to have a metal and a nonmetal, because that would be ionic. So we have to have our nonmetals. You need to know where those nonmetals are located on the periodic table so that you can double check and make sure that when you're doing an example, do you have an ionic compound or do you have a molecular compound? When we're writing molecular formulas, they are exactly the same. For instance, H2O would be a molecule because it's hydrogen and oxygen, and they're both nonmetals. And the 2 tells us that we have 2 hydrogens, and remember, we don't write ones, but just having that O there means that we have 1. So we've already kind of gone over the whole subscript thing. We've done that in the past. It's important to remember, though, that, like, for instance, when we had sodium chloride, and we had a picture and we had all these sodium and chlorines, and it was 3-dimensional, and they were all bonded together back and forth and side to side, and it was kind of this big cube. You might have to get out your notes if you needed to take a look at that again. But we reduced that down to lowest terms. So we really had maybe 100 chlorines and 100 sodiums, but we reduced it down to 1 and 1. When we're looking at molecular compounds, the number that you have is the actual number. So when we say H2O, we're not saying that we have 20 hydrogens and 10 oxygens and we're just lowering it to the lowest terms. H2O really is 1 oxygen and 2 hydrogens, and that's it. Whereas in the ionic compounds, you really could have had a lot, and we reduced it down to its lowest whole number ratio. So if we take a look at some molecular structures, these are going to show us how the atoms are actually arranged. So when we see H2O, we know it's 1 oxygen and 2 hydrogens, but a molecular structure is actually going to show us how that would look. So it's not, the hydrogens here on the side with the oxygen in the middle. Kind of has this bent shape, and we're going to get into the shapes of these molecules and how we determine the shape. But a molecular structure is going to show you very specifically how they're arranged. Carbon dioxide is more linear, where the atoms kind of go in a straight row across with carbon in the middle and then the 2 oxygens, one on either side. As far as covalent bonding, it is a sharing of electrons. The octet rule is still going to apply. There are a few exceptions that we'll get into in video 2. But a single covalent bond is just 2 electrons that are being shared. So for example, if we look at hydrogen, and remember this is a diatomic, so we have hydrogen bonded to another hydrogen, you can see that neither one of them have their lowest energy level full. So hydrogen would be happy with 2 electrons just because 1s can only hold a total of 2. So what you have is the 2 hydrogens, and we have their dot diagrams here. And instead of them gaining or losing electrons, we're going to show that the electron here is, it's going around both of these hydrogens. And so instead of the electron going only to one element, these electrons kind of go equally back and forth between the 2. And so there's where the sharing comes in. You don't have one, they don't each have 2 of their own. They're sharing the 2 there in the middle back and forth. Oxygen, if we take a look at the dot diagrams, we have 6 dots on oxygen, and hydrogen just has the 1 each. And if we take a look at then what it is when they actually are sharing, this hydrogen and oxygen, they each have to have 1 to share. So this electron on oxygen is going to get shared back and forth, and the electron on hydrogen is also going to get shared back and forth. And then also for this one, so we can have this sharing that's happening here. When we draw that dot diagram, you're going to notice the 8 dots here around oxygen for its octet rule. Hydrogen's happy with 2, so hydrogen had 1 of its own, and it's also sharing 1 from oxygen. So hydrogen has 2, the oxygen has 8. If we take the shared pair of electrons here, if we take that out and replace it with a line, that line is representing the bond or the attractive force that's holding the oxygen and the hydrogen together. And we call those structural formulas. They will replace the dots with a dash mark to show the bond holding those together. So for hydrogen, instead of again having the 2 dots in between, we now have this dash mark. For the water, notice that it's not in a straight line like this. We will get into being able to determine the fact that it has more of a bent shape. That will come in a future video. But again, those dashes represent the bonds. And remember, oxygen would also have 4 electrons that aren't being shared with anything, that are oxygens only. And those unshared pairs are called lone pairs, non-bonding pairs, when they're not being shared with anything. So these 2 groups of electrons, since they're not being shared with the hydrogens, are called lone pairs. Okay, that's usually the way I'll refer to them. So oxygen has 2 lone pairs in this case. We're going to finish up on this last slide with double and triple bonds. A double bond just means that you have two of those dashes. So if it takes two electrons to make one bond, then a double bond is going to be two pairs, so a total of 4 electrons in order to create a double bond. And this happens when oxygen bonds with itself. We have oxygen here with only the 6, and each one has 6. And all they're going to do is rearrange the electrons to show that these two lone ones here are now, kind of in the middle, and they're being shared back and forth between the oxygens. And so because you have two pairs that are being shared back and forth, that creates two single lines. Looks like an equal sign. That's the double bond right there between the two oxygens. And those happen frequently. Double bonds are pretty common. Triple bonds are not very common though, but it would be 3 pairs of electrons, so a total of 6. And this happens when nitrogen gets together with another nitrogen. You can see they've taken these 3 unbonded on each, and they've put them here in the middle. So we still have those 6 electrons, but now these 6 are being shared back and forth. So this nitrogen has 6 plus 2 of its own, these 2 over here, and then this nitrogen also has those 6 that are being shared plus 2 of its own, and so we get a triple bond in this case since we're sharing 6 total electrons.